All right, we are going to go ahead and get started. So hello everyone and welcome to Striking Back, hunting Cobalt Strike using Sysmon and Sentinel. Before we get started, a couple of housekeeping notes. This webinar is being recorded and we will be sending out a recording to everyone who registered as well as some extra materials. We will be answering questions at the end of the webinar, so please feel free to type those questions into the question box or into the chat. And now a little bit about binary defense before we jump in. Binary Defense is a managed security services provider and software developer with proprietary cybersecurity solutions that include SOC as a service, managed detection and response, security information and event management, threat hunting, and counterintelligence. With our human-driven technology-assisted approach, Binary Defense is able to provide clients with immediate protection and visibility, combating and stopping the next generation of attacks that businesses face. Our speaker for today is Randy Pargman, and I'll go ahead and hand it over to him to start the presentation.
All right, thank you very much, Emily. Very nice to have you all along for this webinar today. My name is Randy Pargman. I'll introduce myself and then we'll get right to the topic. I am the Vice President of Threat Hunting and Counterintelligence at Binary Defense. I've been in this role for a little over a year, and before Binary Defense, I worked for the FBI as a computer scientist on the Seattle Cyber Task Force and with the Cyber Action Team. Worked for the FBI for 15 years, had a great time getting to the bottom of intrusions to identify the threat actors who are behind those and bringing them to justice. At Binary Defense, I focus on stopping those intrusions before they become a major crime scene that the FBI has to come help with. So really happy about all the work that I get to do, the great people that I get to work with at Binary Defense, and also really happy to get to share information with the information security community and things that we've learned along the way that can help other people. So not just in this webinar, but if you ever want to reach out through Twitter, LinkedIn, or whatever, I'm happy to have conversations with any other threat hunters or researchers, share things that we've learned, and hopefully put a stop to all of those threat actors before they do a lot of damage. So let me go to the next slide. There we go. All right, before we start talking about Cobalt Strike, I wanted to make something really clear. Cobalt Strike is an offensive security tool, a red team operators tool that is commercially supported, and Cobalt Strike is great. It is not the enemy. I love working with red teams. It is absolutely phenomenal to have some trustworthy people who know how to break into systems the same way that threat actors would do, who are on your side, breaking into your own systems in a safe way, and then telling you about all those ways that they did it so that you can defend better. That's the whole point. And Cobalt Strike makes their job a whole lot faster and easier. It shouldn't be that every red team operator has to come up with things from scratch. So Cobalt Strike is not the enemy, and I don't want to cast a negative light on that. However, it has become increasingly obvious through actual incidents that we've investigated that threat actors also love Cobalt Strike. They are not paying for the license. They're not legitimately accessing it. They're using cracked and pirated versions. And just like any software can be pirated, Cobalt Strike can be too. And part of my team's job is looking at the criminal forums where people who are interested in breaking in and stealing things trade information with each other. And we've seen many times that cracked versions of Cobalt Strike have been made available. So we know that this is widely available, and practically we're seeing it used in actual intrusions against victim companies. And where Cobalt Strike usually comes into play is after the initial access. So there will be some kind of a botnet binary that's dropped, or there will be some loader that is delivered either through a malicious Word document, Excel spreadsheet, or a zip file that contains a batch script or something like that to run. That will usually deliver the initial loader, and then the loader will do some surveying the system, and if the threat actor decides this is where they wanted to land and this is a legitimate victim they want to land on, a little while later there will be a drop, and that drop is very frequently Cobalt Strike. The reason is because it's an awesome tool. It's something that threat actors can do a lot with. There's a whole lot of customizations available. And so it is worthwhile because threat actors are using it so much. It is definitely worth your time as a defender or a threat hunter to know how it works, at least on the side of observables, things that you can see from workstations that might be victimized, and then know how you can defend against it. This is an ongoing research project. Like, I looked at the information shared about how to detect Cobalt Strike from 6 months ago, and it was already pretty much out of date because threat actors have gone on to a newer version of Cobalt Strike. Cobalt Strike is under constant development, as well it should be. It's a commercially supported product, and so you can expect that it's not going to stay still. It's a moving target, but that's why all of us in the information security community need to share good information with each other. We need to keep up to date with what are the latest techniques and what are the latest detection techniques. Share those amongst each other so that we are not caught off guard when Cobalt Strike is running in our environments. So I also want to say that it is most useful to focus your detection efforts on techniques rather than on tools. What I mean by that is a detection around a tool would be something that only works if somebody is using some particular settings for some particular tool like Cobalt Strike or like PowerShell Empire or something like that. And if the threat actor is using any other tool, that detection isn't going to work. Those are kind of brittle tools or brittle detections that don't give you as much value as you might like. It is much better to write your detections around techniques. These are things that threat actors might be doing across multiple tools. Like, it's not just going to detect this version of Cobalt Strike, but it'll detect also Meterpreter, or it'll detect ICE ID or whatever else, right? So those are the high quality detections we want to focus on. However, when you have a tool that is as widely used as Cobalt Strike, it is definitely worth your time to look at some of those low hanging fruits, those easy detections that you can get around the tool. If it doesn't cost you a lot to implement the detection for a tool, and you know the tool is used a lot, you might as well put those detections into place too. The nice thing about them is they're usually very specific, so they're high fidelity, low noise. Those tool detections, even though they might be brittle, they're not going to throw a lot of false positives. They're probably just going to give you a high confidence alert that this tool is being used. So in this webinar, I'm going to show you both. I'm going to show you everything that we've learned recently over the last couple of weeks in engagements against threat actors using Cobalt Strike, and hopefully this will be helpful to you. So let's get into the actual hunting queries. I also want to say I'm about to show you a whole lot of queries, URLs, tips and tricks. Feel free to take screenshots if you want, but I'm also going to put together a document that has all of these queries put together for you in a nice, easy to use format, and we're going to email those to everybody who signed up for the webinar. So you'll get a document, kind of a cheat sheet with all of this stuff, so you don't have to retype it. But feel free to take screenshots if you want to. So our hypothesis for these threat hunts is going to be that many actors, many threat actors, use Cobalt Strike with the default settings. What I mean by that is, if you're not aware, Cobalt Strike has a lot of customization features in it. It has malleable profiles, it has the artifact kit. These are all things that the operator of Cobalt Strike can go in before they deploy it and make changes to the way that it looks in order to make it hard to detect. Any sort of changes like that are going to break your tool-specific detections. But what I've found through study, and I'm going to show you the results of that study in a minute, is that a whole lot of threat actors are deploying Cobalt Strike servers and stagers with configuration files that are exposed to the public if you know how to get them, and that contain the default values. Like, it's overwhelmingly default values. These are lazy operators, but apparently that still works for them, so they don't really have to try that hard. Anyway, that is an opportunity for us, the threat hunters, to detect those default settings, and we'll figure those out not by having a copy of Cobalt Strike, but just by observing what actual threat actors are doing when they're getting Cobalt Strike delivered to victims. What I also want to point out is we're not trying to defend against red teams. Red teams are on our side, a very helpful resource. I really don't care about detecting those, although that's a nice validation that your detections are working properly. If you have a red team engagement and you're catching them lots of different ways, that's good for you. Hopefully the red team will try harder and show you those places that you don't have detections. But what we're trying to do here is detect threat actors. So I'm going to give you a sneak preview of what we're going to go over, just a high level. We're going to look at patterns of net flow. And right off the bat, I want to tell you this is the best detection in this whole webinar. This works not just on a tool, but across pretty much anything, any remote access Trojan that has regularly recurring connections back to its command and control server. This is the best way and the most reliable way to detect. But we're also going to look at some other unusual things you might not have thought of, like when there's process injection, what's the thread start address? That's actually a useful observable that you can detect on. We're also going to look at the default names of named pipes for Cobalt Strike, and a big shout out here to the developers of Cobalt Strike who put this stuff out on their blog. They talk about what those default names are, and they're aiming that blog toward a red team operator so that they can change those names that they know that they're detectable. But for a defender, it's really useful to know what those defaults are in case the threat actor doesn't change them. That way you can use that to detect them as well. We're going to look at open source research that we can do for Cobalt Strike beacons that are staged publicly. We can go out and grab those configs and we can get a lot of value out of that. And I'm going to show you those results. I'm also happy to share some of that raw data with any other researcher who's interested. We're going to look at files that are named like system utilities, but they're in the wrong location. We'll look at user agent strings. This is something you need network visibility to actually make use of, but it can be useful if you've got that. And then we're going to look at some linear regression analysis to show anomalies of events of Sysmon event ID 10, which is process access. This is also something kind of surprising, something you might not have thought of, but it's a really great detection as well. And that also will work against not just Cobalt Strike, but other tools as well. So let me start right off with the most useful detection. If you do nothing else, this is something that I highly recommend you invest some time putting into place. And that is looking at the pattern of regularly recurring outbound network connections. This is something that when we get into the research about the exposed Cobalt Strike Beacon configs and the timing, it's going to be even more obvious why this is useful. But here's the pattern that we're looking for here. We're looking for any internal system that is making communications or it's making network connections to external systems, and it's doing that multiple times on a regular basis. So like every 60 seconds on the dot, this process, let's just say it's a legitimate PowerShell.exe, is connecting to this external IP address and it's doing something. You don't even know what the something is. Let's say that the communication is all encrypted. You don't have a TLS man in the middle. You just know that there is a connection being made. The very fact that there is a connection every 60 seconds on the dot should get your attention. That should get your attention to look at the process that's responsible for that, investigate what else it's doing, and figure out if that process is supposed to be running there, if that's allowed or not. Quite often, we see these coming from legitimate Microsoft signed binaries. So there's nothing about the program itself that looks suspicious, but it's a binary that has been injected into, or it's running a script, or it's doing something else that is under the threat actor's control. So the way that we look at this is by analyzing the timing of NetFlow. We just need to look at when our connection's being made, source and destination IP address. That's it. If we've got some more information about what process caused that, that's even better. Or if we've got some information about what computer that came from, regardless of the source IP address, that's also really useful for getting to the bottom of things really quickly. So there's a couple of different ways you can do this. I'm not going to get into the nitty-gritty details, but if you have network monitoring and you're using Zeek, which is a free open source tool, you can use another free open source program called Rita, which I've given a URL for there on the top left side, to run some analysis against the Zeek logs, and it'll automatically compute scores to tell you how likely some communication is to be a beacon, and then it'll give you those results, and then you can go hunt those down. If you don't have Zeek and Rita, but instead you have something else like Sysmon, or you have Microsoft Defender for Endpoint, you can use a threat hunting Jupyter notebook that I created, and there's a whole nother webinar that I gave just last month. You're welcome to sign up and review the recording of that if you want the details, or you can just go to our GitHub and download that, and hopefully there's enough information right there in the notebook that you can put that to use. The chart that you see in the middle part of the screen, that is one of the outputs of this Jupyter notebook that will show you communication pattern over time. And this pattern right here, that is clearly a beacon. Kind of starts out small, but then it gets pretty noisy, and it's very regular. There's, every 10 minutes, there's 6 connections. And this is something that will rise to the top of detections within about 15 minutes of the malware first starting out. And we've tried this with lots of different varieties of malware, but especially with Cobalt Strike, it rises up really, really fast. So the metric that we use to measure the beacon-like properties of the network communication is this score. And you can see down at the bottom of the screen, this is another output from that Jupyter notebook. And it'll show you that between these 2 IP addresses, there was a score of 0.934 out of 1.0 being maximum, that this is a beacon. That should definitely get your attention if you get something like that. Now, that process might be something that you expect, right? It might be something that you deliberately set up to go out and check every 60 seconds or once every hour, or once every 90 minutes. All 3 of those situations, by the way, will produce this really high score. It doesn't matter what that interval is, it's only looking at how regular the interval is. So you might have something legitimate that's set up to like check for updates or download some updated data for your database or whatever. That's fine. You can identify that, whitelist it, make it something that you're no longer alerting on, and move on. Once you get that baseline of the things that you expect to be beaconing on your systems, now you can just set up a good alert, and anytime a new beacon pops up, you can go investigate it. So those were the systems, the Rita and the notebook that I presented last time. Since then, just in the last week, I've put together a new KQL query that can do a lot of this. It's not quite as sophisticated, but it gets really good results. I'd say I'm 95% satisfied with this query. The great thing about this query is that you can actually make this into a Sentinel alert. So you don't need to have something that you go proactively out and you search for the beacons. Now you can have something that will alert you when there's beacon-like behavior that's detected. So I want to go over this query just so that you understand it. Again, don't worry about trying to copy all of this. I'm going to send it to you in the resources after this webinar. But at the very top of this query, we're taking a look at Sysmon event ID 3. That is network communication or network connection started. Now, I want to say right off the bat, you don't need to have Sysmon for this to work. I also made a version of this for Microsoft Defender for Endpoint. So if you've got that, you'll have device network events. You can use that table as the source of this data as well. And I'll send both versions of the query out so that people can have that. You could also, if you have firewall logs shipped into Sentinel, you could run the same query on those as well. Really, all you need to know is the source IP and the destination IP and the timing of it. That's the basic information that you need. So in the second part of this query that I've labeled time deltas, this is really cool. This is something that I just learned about recently in KQL. You can use the serialize function with information sorted to create a time series that then you can do analysis between one row and the next row. So in this case, what we're looking at is we're taking all of the network connections, we're sorting it first by source IP address and then by destination IP address. Or you could sort it by the source system that it came from if you got that information and the destination IP address. And then we're sorting it after that. The third level sort is by time generated. So if you think about it, if you can imagine what this would look like in a table, it's, let's say that my system is called workstation 1. It would be like workstation 1 communicating to IP address A at this time, and then the next communication between my workstation and that same IP address and the next time that it communicated. It'll go through all the communications between my system and that one IP address and all the times in sequential order. what that means is we can now take the difference in time, and in KQL that's date time diff. Date time diff will take the difference between the record that we're looking at and the following record, as long as the source and destination IP addresses are the same. And then it will take all of those deltas and it'll put them into a list. So I don't know if you can see on the results down there at the bottom, the time delta list. This shows you the first part of that list. So you can see like the first one there is 63, 65, 55, 42, 52, 40, et cetera, right? And there were 7,503 of those connections. Those are the times, those are the delta times in second between connections that came one after another. So there was 63 seconds between the first and the second connection. Then there was 65 seconds between the second and third, then 55 seconds between the next, and so on. You'll notice that these time deltas are not precisely the same. This wasn't like every 60 seconds on the dot. And the reason for that is because Cobalt Strike and lots of other remote access tools that threat actors use have not only a period that they check in, but also this concept of jitter or a variance. And that's meant specifically to throw you off, right? It's meant to thwart analysis that's looking for communication that happens every 60 seconds on the dot, because it changes it by 10% each time. That's why you see that variance. However, the next calculation that we're doing in this KQL query is standard deviation. This is something that's built into KQL. I haven't used this a whole lot before, but this is one of my new favorite functions in KQL because it makes things stand out, or it tells you if things are very regular or not very regular at all. So I'm not going to get into statistics and what standard deviation is, but let's just suffice it to say the lower the number, the more alike the numbers in the series are. So even though we've got these different numbers like 63, 65, 55, 42, when we average it out over like 7,500 of them, they all cluster around 60 seconds. Like they're pretty close around there. And so their standard deviation is really low. It's 2.012. So that bubbles it up to the top of our list. And then you can play around with the standard deviation threshold that you want. I found that looking at a standard deviation of about 100, so any standard deviation score that's under 100, and any pair of communicating hosts that has more than, I think I set it to like 15 or 20, but you can play around with that too. As long as there's more than so many connections and the standard deviation is really low, then you can identify very quickly these processes that are evil. And the thing that I can tell you about every single one of those results that shows up on the screen I'm sharing with you, every single one of those was Cobalt Strike. When I ran this against some other piece of malware, it identified those just as well. So anyway, this is super powerful. I hope that you'll put this into place. There is a commented outline there that is just looking at whether you care. If you uncomment that line, that means you care only if the beacon is currently going on. It looks like right till the current time to see if that beacon is still happening. And if something happened in the past, it'll ignore it. I pretty much want to see if there was a beacon at any time, so I commented that out, but I wanted to leave that in so you've got the option. All right, so the next thing that I want to look at is another statistical method. This type of method is using linear regression to look at not standard deviation, but how many events per second or how many events per minute, or in this case, I've done how many events per hour are normal to see per workstation, and then noting anomalies. And this is something else that's built into KQL, so you can make use of this without doing anything fancy. If you've got Azure Sentinel, you can just put this into you can put this to work for you right away. Sorry, tripping over my words. So the way this works is it's trying to do a line fit to the normal frequency of a Sysmon event ID 10 per hour per system. And then it's looking for anything that is way off from that line that fits. So I've included a small picture that kind of shows you in the bottom left corner of the screen. You can see a whole bunch of red data points, and then there's a black line going through them that is kind of a best fit line. That's kind of what KQL is doing for you, or what Sentinel is doing for you on the back end. It's trying to fit a line, and then it's noting for you anything that is way out of base for that line. So in this case, what we're looking at is Sysmon event ID 10, which gets recorded when one process opens up another process and then tries to access that. And that could be for read access. It could be like a antivirus program. And in fact, in my research, I found there's a lot of antivirus programs that do a lot of opening up other processes to look at them. You would expect that. That makes sense. But what surprised me is that during Cobalt Strike running on victim system, this event ID 10 spiked tremendously. And in fact, it was in a really short amount of time. So what I wanted to show you is that top row right there that shows that the baseline of number of event ID 10 occurrences per hour for this system is 158. So as we go along, normally this system, for whatever reason, has about 160 of these events per hour happening. And then in this anomaly, we see that there were 31,181 event ID 10s in that 1 hour. And it highlights that hour for me and what computer it was on. This generates a score of 307, which is way above my threshold of 150 that I'm looking for here. But what really should get your attention, like the eye-popping number here, is 160 versus 31,000. Like, that is an insanely big spike. That is not something that you can easily miss. Now, somebody's asking, what was the threat actor doing? I don't know. They were on the other side of the keyboard where I can't see them, so I have no idea what it was that they were doing, but I did dig into this a little bit more, and I wanted to show you the results. So narrowing it down, I found it wasn't just that huge spike in an hour. It was actually within 5 minutes. So you're going to see in this query that I did, I'm looking at event ID 10 for the computer that I was looking at. In fact, I don't think I've got that filtered properly for the computer, but regardless, it still shows the results that I was looking for. So between 6 p.m. and 6:05 p.m. UTC on February the 3rd, these were the number of events between the process that caused them and the target process. So you can see the top one was targeting Firefox for some reason, and then it was accessing Teams, it was accessing Runtime Broker, PowerShell. There was an SI host in there as well. You can see these numbers are like off the chart. Remember that the normal line fit for this system is about 160 events per hour. And all of these are the number of events that happened within 5 minutes. So I would say that this is a really good detection. I would love to know some more, like the curious side of me who wants to know how everything works. I'd like to know what was going on in Cobalt Strike that it did this pretty noisy thing. I don't know, and I don't think I can know. But what I do know is that this is a pretty good detection. The other thing that you should keep in mind, though, unlike the traffic pattern analysis, this didn't occur like right off the bat. This wasn't something that happened as soon as Cobalt Strike ran. This was obviously something that the threat actor did, like some button they pushed or some script they ran. I don't know what they did, but this isn't something that's gonna pop every single time. So that's worth noting. As you're looking at your different alerts, if you just put this one into place, you could definitely have a threat actor using Cobalt Strike doing whatever else they might do and never hit this alert. So just keep that in mind. All of these alerts kind of go together and they support each other. The next thing that I want to bring up, this has been really useful, and for me, not being a red team or not having access to Cobalt Strike, this gives me a little bit more visibility into some of the inner workings and at least what people are doing with configurations in the wild. So there's a whole lot going on the screen, but I just kind of want to take it one at a time. So first, this observation. When I've talked to red team operators who use Cobalt Strike, they tell me that their standard operating procedure is to lock down their Cobalt Strike server so that it can only communicate with the IP address range of the client that has hired them. That's a safety mechanism. It's a good idea. It's best practice for a red team to not accidentally infect somebody else, because once you put exploit or a delivery mechanism to deliver your payload out into the wild, you don't really know what the victim's going to do with it, or the target is going to do with it. They might send it to somebody else, and you don't want to accidentally, as a red team operator, you definitely don't want to accidentally get access to somebody's system who did not hire you. So generally speaking, when you do this research, you're probably not going to find a whole lot of red team operations that are going to answer to your IP address that you're scanning from. There are a couple of different ways to do this. I focus on Shodan. There's also some other systems that'll do this, or some people have active scanning going on, but I'm just using Shodan, and I'm looking a couple of different ways. The easiest and most straightforward way to search Shodan, as long as you're using the beta Shodan version, is to use JARM. And I put on there put on the screen a link to a GitHub that has JARM hashes for a whole bunch of known malware servers. Like Cobalt Strike is on there. That's the JARM hash that I've listed. It also has Meterpreter and a whole bunch of other ones too. So definitely check out that GitHub, super helpful. And that will let you know what sort of things you're looking for. JARM works to fingerprint TLS or SSL profiles of servers. So you can run it against a domain name or an IP address. And I've got on the bottom of the screen a little screenshot from my terminal as I was running JARM as a Python script against an active Cobalt Strike server. This is one that I retrieved a config from, and I'm going to show you that in just a minute. But this is really, really useful. I want to suggest a couple of different things that you can do with this. So one is you can search Shodan for this JARM hash. And as you can see on the left, when I searched Shodan a couple of days ago, there were about 6,800 results. You need to have a Shodan license in order to download all of those results. But you can take that and it'll give you a list of IP addresses and port numbers that are matching the profile of a Cobalt Strike server. That doesn't mean that it is for sure. There are definitely some false positives that I found in that list, but a whole lot of them are, and it's at least a good candidate list to look at. You can update that on a fairly regular basis, and then you can use that list of IPs to flag communication for a closer look. You can also do something proactive if you want, because you have to understand Shodan has all these scanning hosts all over the world, and they randomly select IP addresses and ports to scan. So that doesn't sound like a really efficient way to do it, but it is. It actually works really well. But there is always going to be some delay, and it's a delay you can't really predict. It might be a few days, it might be a couple of weeks between scans that might actually flag a server as being Cobalt Strike. In that in-between time, between the last time that Shodan scanned that IP address when it wasn't a Cobalt Strike server, and today, when that might be attacking you, you might not have that intelligence from Shodan. So something else that you can consider, if you put this together with that other detection, where you're looking at beacon-like behavior, or even just any communication with any IP address that happened, more than 10 times. Let's say that that's a reasonable way for you to narrow down your list of IP addresses. You could actually use something like Microsoft Logic apps or playbooks hooked up to Sentinel to automatically take those alerts of communication from your environment out to some IP address that you haven't seen before. You could send that over to a web server through a webhook that will kick off a JARM scan, just like I showed on the bottom of the screen. It's really easy. You can run JARM yourself, and then you can get the JARM hash for that, and then you can have your Logic app get the result back from that JARM scan, maybe add it to your Sentinel ticket or something like that. So there's ways that you can hook this up, and you can enrich your data by looking at the JARM hash of anything that is communicating with your environment on a regular basis. And then you can have a list, like I would recommend you look at that GitHub again, look at all the list of JARM hashes that might be malicious or that might indicate a malicious server rather. Nothing malicious about JARM or its hashes. But look at that list and then have that worked into your automation too, so that you get an alert if you're communicating with something and the JARM hash matches. All right, next I want to give you some results from my survey of publicly available Cobalt Strike Beacon configs from staging servers. This is something I've also talked to red team operators about, and another best practice is that red team operators should not have publicly accessible staging for the configurations of their Cobalt Strike beacons. But it seems that threat actors don't really care. They put these things out in the public. And what I did was take the list of candidate IP addresses that were identified through Shodan as being possible Cobalt Strike servers. And then I used the in-map script that I've got linked at the bottom of this page. It's on the next page as well. And using that script, I was able to query each one of those IP addresses as if it were a stager calling back to get the next payload. And basically what that will give me is the configuration of the Cobalt Strike beacon that's hosted there. So again, if you know nothing about Cobalt Strike, that might sound kind of confusing. If you know about it, that's really basic stuff. But here's what I did. I took a look at all of the beacon configs that I could pull down recently. This was from data, I think 2 weeks ago I ran this the last time. And I looked at the configuration options like the polling interval. This tells Cobalt Strike Beacon how often to check back in with its command and control server. You can see overwhelmingly there, 60 seconds, which is the default, was used. So over 71% of the 2,400 or so beacon configs that I was able to pull down, most of them had 60-second intervals. Looking at that other pie chart, you can see the jitter setting. The jitter tells you, how irregular that connection might be. 76% of them had no jitter at all. So by far and away, the most popular setting for threat actors using Cobalt Strike is 60 seconds, no jitter. That's going to stand out like a beacon, like a very bright beacon in your results looking for network communication patterns. That's why I really want to hammer that home, because that is such a valuable technique to use. What really confused me, or at least made me wonder what the threat actors were thinking, is the second most often used polling interval, 5 seconds. That means every 5 seconds, the Cobalt Strike beacon is calling back to the command and control server. That's going to produce a huge anomaly just in number of connections. I mean, even if you're not looking at polling interval, or you're not looking at the regularity of connections or standard deviation or anything like that, like within 10 minutes, you're going to have so many communications because they're every 5 seconds. You can see that the others were also pretty short, like 30 seconds, 10 seconds, 3 seconds. In that all others, there were a whole bunch of varieties that I don't know, they were just kind of random numbers picked. They were all around 60 seconds to about 150 seconds was the longest. So what I took from this is that for whatever reason that I can guess, but maybe not fully understand, threat actors want pretty frequent polling or beaconing back. The reason I guess is because the threat actors don't want to have to wait around if they issue a command to a client beacon. They don't want to, tell it, give me a directory listing, and then have to wait for 5 minutes or 10 minutes to get a result back. I don't know. I haven't been a red team operator, but I can imagine that would be frustrating, and that's probably the human behavior that's driving some of these decisions. But as defenders, let's take advantage of that. If they're going to be beaconing back every 60 seconds or 5 seconds, let's definitely detect that. Next thing I wanted to show you was also pulled from the beacon configs. So there is in each config a spawn target for x86 architecture and for x64 architecture. Looking across both of them, they were very similar, so I'm just going to show the x86 as an example here. One guess, what do you think the default setting is if you don't change anything in the malleable profiles? you probably guessed, it's run dll32.exe. What that means is that Cobalt Strike Beacon is going to try to inject itself as a new thread inside a run dll32 process, or any of these other ones like MS TSC or GP update or MAV inject or DLL host, WRFALT, which is the error reporting system. So you can see threat actors do modify this. It's not like you should just look for run DLL32, but this is interesting. So the other thing that I have to say I don't fully understand, not being a red team operator, is when this happens. And just based on observations, we had some actual threat actors deploying Cobalt Strike or loader that would result in Cobalt Strike in an active campaign that we studied. In one case, as soon as Cobalt Strike ran, in fact, I'm going to show you this in a minute, but like within a couple of minutes, it injected into other processes. And then in some other cases, it just ran from the original process that we launched, and it didn't inject into any other processes for a long time until later on, I think, when a threat actor came and got hands on the keyboard interactive. So I think just based on observations, this must be something that can be set up to either go automatically as soon as it spawns, or maybe later as the operator directs it to. But one way or the other, you definitely need to look out for a process injecting into another process. So let's take a look at that. Process injection patterns. This is a timeline of a Cobalt Strike beacon that was named sihost.exe. Now, what you'll notice right away if you look at the process path is that although sihost is a system program, like this is a system utility, this one is not the legitimate Microsoft one. It's just named the same. The file name is the same. That's it. It's not really disguised very well at all. So this is a detection you definitely need to look at quite outside of process injection. If you've got some system utility file names that are running out of weird locations like downloads, then you definitely need to take a closer look at that. But look at the timeline here. So at 1729, this process started. It did a couple of DNS queries. By the way, one of those was for the command and control server's domain name. The other DNS query was for the workstation that this was currently running on. It was querying the domain controller to get the IP address of the host that it was currently running on. That's another pattern that I've seen. I'm not sure if that is across the board reliable, but it's an interesting pattern as well. And then notice, so it started at 1729.21, and then at 1733.44, so just a couple minutes later, it started injecting some remote threads into explorer.exe, service host, and dll host.exe. So if this had followed the pattern of the most popular configs, it probably would have injected into run dll32. But in this case, the threat actor had set up the config to inject into DLL host. I also suspect that what's in the config is not the only option. Just because it's in the config, that doesn't mean that's where it's definitely going to inject into, but it's worth looking at. And then also notice that at 1733.57, the process was terminated, and at 1733.59, the file sihost.exe was deleted. Looking into this closer, we found that it was actually Microsoft Defender antivirus that had killed this process. So Windows Defender or Microsoft Defender actually did its job properly. It detected this malware, and in fact, this is pretty cool. It identified it as Cobalt Strike in the event, and it killed the process and it deleted the file. Unfortunately, Defender acted just a little bit too late, because just before it killed this process had injected into these other processes. And then as we continued to watch this, and by the way, this was not on a real life client system that we were just casually watching this going on. This was actually a testing environment that we set up to simulate an Active Directory environment with a bunch of computers. So don't think that we're just doing research on client systems. We're actually doing this research to inform our defenses so that we can stop it earlier on client systems. Just wanted to make that really clear. But anyway, as we watched this go on, that DLL host process was the one that continued on, and then that started beaconing back to the command and control server. And Windows Defender never identified DLL host process as being malicious because it had been injected into. So here's the interesting pattern, and I want to give full credit to a team member on my team, James Quinn, who noticed this and pointed it out. I've been looking at this data and I didn't notice that this was an interesting pattern till he said it. And then we started doing a whole bunch more research and found this pattern holds. And that is when Cobalt Strike, and actually when a lot of other malicious processes inject into another process, the thread start address is often kind of random or unpredictable in the high order bits. But when you're looking at the last 4 digits in the hex representation, so the rightmost 4 hex digits, it's usually less than 1000. It's probably going to take some more research to understand why and what other patterns we need to look for. But in a whole lot of Cobalt Strike, we actually saw that the last 4 digits being 0000, like exactly right on the dot, and thought that was the pattern at first. But then doing more experiments and letting more threat actors run more Cobalt Strike, we found it wasn't always exactly 0. So this is the query that we're using right now. It's not free of false positives though. The things that have come up in real life client environments when we've run this query have also included antivirus injecting into other processes to inspect them. And oh shoot, what's the other one? There's been a couple of others, but the instances of this are fairly low. Like in a very large client environment with thousands, tens of thousands of endpoints, there's not many alerts like this. I think maybe like 1 or 2 a week is what I've been getting. So not bad. Like you can definitely investigate these. And then it's really easy to spot the processes that are supposed to do this. If it's antivirus that's doing it, you can just add that to your ignore list, and then the rule won't detect on antivirus doing it anymore. Every once in a while, a process comes up that kind of surprises me, but it's worthwhile to go investigate each one and see what's going on with it. So that's another really useful but not intuitively obvious pattern that you can look for. The next one is squarely in the camp of tool detections, which is why I put it near the end. This is something that is going to break. It's not going to last forever. And in fact, the very fact that on the Cobalt Strike blog, there is all this information about what these default names are for the named pipes, how they work, and what red team operators should do to change these. It's pretty easy to change a lot of these pipe names. Based on all of that, I can pretty much guarantee that these are going to change. So this is maybe a short-lived detection. However, it's an easy one. There's static names we can look for that are going to be really low on the false positives, very high fidelity alert, and not generate a whole lot of alerts. So might as well put it into place. This is something that we're definitely doing. Look at any time that a named pipe is created, and if you want to know more about what named pipes are or why they might be created, feel free to go look at that blog. It's super interesting. But just at a very high level, this is for communicating within processes, or you can even use it to do like a remote pipe on another system, I believe, to communicate that way. But these are pipes that Cobalt Strike names that follow very specific patterns. And so I've got a KQL query here that will just detect all of those default naming patterns. And if any of them show up, it will alert you. And then you can definitely take a look at that and see if it's Cobalt Strike. In the results here, all of these things were, in fact, Cobalt Strike. The other thing I want to point out about this detection is, like some of the others that I've pointed out, this doesn't happen right away. Like this isn't default behavior. Cobalt Strike doesn't need to use pipes. The threat actor gets to decide, or the operator of Cobalt Strike needs to decide, I'm going to do something that would create a pipe and connect to it. So it's a good detection, but you can't count on it to be an early warning. That's useful to know. Next thing that I wanted to point out is user agent strings. So I looked across all of the Cobalt Strike Beacon configs that I was able to pull down from public servers. And then I looked at the user agent that was configured in that beacon config. And then I just sorted those to see which ones occurred most frequently across all of the ones that I'd collected. So these are all presumably threat actors' use of Cobalt Strike. If they're red team operators who are exposing their beacon configs to the public, then they should probably work harder at being a stealthy red team. But I presume that most of these were actual threat actors. I frankly was surprised. Like, I thought that pretty much every red team operator or threat actor would take the time to pick a user agent string that would blend into an environment. And you can tell that, I mean, a lot of these look like they probably sort of should, like they look like browser user agents, but look at the actual values, like Internet Explorer 11 on Windows 7, or WebKit on Windows 7, or Internet Explorer 8 on Windows XP. I mean, as a defender, as a threat hunter, if I had a legitimate employee with a workstation that was running IE8 on Windows XP, like, I would want to know about that. That would be a finding all in itself. But I think these really stand out. If you are collecting user agent strings, like from your proxy log or your HTTP proxy log, or if you're doing deep packet inspection, you can collect these. This is great. Now, as far as the deep packet inspection thing, I do want to point out almost every single one of these Cobalt Strike beacons had a TLS certificate. So it was going to be encrypted unless you are doing TLS termination and man in the middle to inspect the traffic on your network. You're not going to be able to see anything from most of these. I mean, there were very few that operated over HTTP without some encryption. So this is a challenge in collecting it. But that aside, like, if you have this visibility, if you are collecting user agent strings, you definitely need to mine this data, because there's some really funky looking user agent strings that Cobalt Strike operators use in the wild, and these should definitely stand out. The next things that I want to point out, these are really simple, so I won't get into them too much, but just looking for any malware that's named itself like a system utility, but it's running out of the wrong place. I just gave one example here of SI host. Obviously, there's a lot of file names that you'd want to put into this detection, but just look at what normally runs on your system and where it's supposed to run out of, and then detect if there's something that is named that running out of somewhere else. This is not Cobalt Strike specific. It just happened to show up during this Cobalt Strike research because somebody used SI host as the delivery file name. But this is just a good reminder. This is a good detection to have in general. The other thing that you can look at, this is sort of flipping this the other way around, is system utilities, legitimate system utilities that have been copied and renamed somewhere else. So usually you'll see something like MSHTA or PowerShell running some script or an HTML application that contains all of the threat actors' backdoor code. But a lot of defenders have alerts set up for conditions like if PowerShell is the process name and then it's doing this, or if MSHTA is running and it's anything but that, then alert. So this is a threat actor technique used to take a legitimate system utility from where it's supposed to belong on the system, copy it somewhere else and rename it, and then run it. So oh, sorry, I lost my train of thought. Oh yes, the thing that you're going to see is a legitimate signed Microsoft binary, like it has a legitimate signature or a legitimate certificate for the program itself, but it's just going to be running with the wrong name. And the way that you look for this is looking for the original file information, original file name, description. This is stuff that you can get from Sysmon, and as of just, oh gosh, like 2 weeks ago, made me so happy when this came out. Microsoft Defender for Endpoint also integrated this in as well. So you can look at any sort of system utility that a threat actor might copy and rename. For example, I've seen cscript.exe renamed as Microsoft.com and put into the user's contacts public contacts folder before. So I've reached the end of the things that I wanted to highlight for you, and fortunately that's also the time that we've got just a little bit of time for questions. I'm going to go through some of the things that have come in, but if you've got any burning questions you want to ask, make sure you put them into the question interface on GoToWebinar. So one of the questions is, join the call late, can we access this recording? Absolutely. After this, you're going to get a link in a couple of days probably to download or to view a video of this recording anytime you want. I'm also going to send out a cheat sheet that has a lot of these URLs that I was mentioning, the text of the KQL query, so that you don't have to retype those. Got some comments about the bizarre amount of event ID 10 calls, I think. I agree, it's a huge and very bizarre amount of calls. Was there anything in the call trace of use? Like I said, I'm not really sure. I haven't investigated probably as much as I could on the endpoint side to understand why that was happening. I am really curious too, but ultimately I don't need to know the answer to that to put the detection into place. So I'll keep studying that, and I will definitely let you know if I get any results of that research. Let's see. Oh yeah, somebody else also mentioned Defender for Endpoint has these new fields. This is fantastic. Using the original file name is super helpful in Defender for Endpoint. A lot of these same things that you can do with Sysmon, you can do with Microsoft Defender for Endpoint. There are some specific things that you still can't do that you need Sysmon for. But I want to encourage you to think about this idea. If you've got Defender for Endpoint, which is a great endpoint product, think about deploying Sysmon side by side. Maybe you can do a reduced config, or at least think about what you want the Sysmon config to be to supplement those things that you're not getting, and feed it all into Sentinel, and then you can query it all together. You can use all these different artifacts and observables from both Defender for Endpoint and Sysmon all together. Got a couple of just comments. The user agent anomaly was really useful. Yeah, definitely good to look at that. That's something that is not just for Cobalt Strike. This is not a tool-related hunt. This is really a technique-related hunt. And the way that you need to do this, really, if you've got access to user agent strings, is do some calculation of what's normal. Look at the user agents that you normally see in your environment. Allow list all of those, don't just ignore them, and then just note any new ones that come up. I don't know if you've ever done it before. I've done a lot of hunting on user agent strings, and you find the weirdest stuff. Like, there are so many weird user agent strings. Everyone is kind of an adventure chasing it down to find out what is this thing. But if you notice, just looking at the way that Cobalt Strike actors normally do the user agent string, it's probably going to be one that sort of blends in to, or they're trying to blend it in kind of to look like it's a web browser. So if you start with that, like, just ignore all the ones that don't start with Mozilla. That's at least a good way to start. One last comment, and then we've got to end because we're at time. Oh yeah, one of the big issues with Defender at the moment is the sampling of the network connection events. Hope they resolve that soon. It is generally true with a lot of tools that I've looked at that if there's some event that happens really, really frequently, they don't always capture every single one of them. They might not capture 100% of them. And I agree, as a threat hunter, I just want to see everything. Like, I want 100% of all the events all the time. That expectation of mine has to be balanced with, how much can we actually consume and store and process, and what the tool is capable of. So I understand it doesn't always get 100%, but in my experience practically working with both Sysmon and Defender for Endpoint, it seems like, as far as I can tell, it's getting the vast majority of those events, and it's been working out really well for me. So that's all we've got time for. Like I said, I'd love to connect with anybody. Look me up on Twitter or LinkedIn, send me an email, whatever. Be happy to continue this conversation. I think there's a lot more to be gained from studying threat actor use of tools, including Cobalt Strike, and a lot of great detections that we can get as defenders. So thank you very much for your time. Thanks for the great discussion, great questions. I'll see you all next time.